right. For those who don't know me, my name is Swapna Srivastava. I'm a Rask Mississauga Center counselor, and I'm on the program committee helping put these talks together. Today, we have a speaker joining us from Japan. He's actually a professor at McGill University, but he is a Saturday morning, and right after this talk, he's going to get his flight back to Canada. So we are very privileged to have him here and be able to speak to him. And it's even more privileged for me. It's my distinct honor to introduce Professor Arun Misra. He was my graduate thesis supervisor, and I've known him for over 30 years. And it's because of him I have my Master's of Engineering from McGill University. Without him, I would not have a career in Canada. So I owe him my professional life to him. So, okay, so Professor Arun Misra is the Thomas Workman Professor Emeritus in the Department of Mechanical Engineering and a member of the Institute for Aerospace Engineering at McGill University in Montreal. His pioneering research spans spacecraft dynamics and control, tethered satellites, space debris, and space robotics. Professor Misra is a fellow of both the American Institute of Aeronautics and Astronautics, that's AIAA, and the American Astronautical Society, AAS. He has been elected to the International Academy of Astronautics and the Canadian Academy of Engineering and serves as a co-editor of the esteemed journal Acta Astronautica. Among his numerous accolades are the Dirk Brouwer Award from the AAS and the Distinguished Service Award from the International Astronautical Federation. Today, Professor Misra joins us from Japan. He's at a conference. Professor, thank you so much for joining us. Please, everybody, give him a warm welcome.
Well, thank you very much. Thank you, Swapna, for introducing me. And I also thank Mississauga Center of RASC for giving me this opportunity to talk to so many young people. You know, as an old professor, I always like to talk, especially when there are many young people in the audience. So today I'm going to talk about asteroids and mission to asteroids. Now, this is not going to be a very scientifically heavy talk. It'll be light, Friday evening talk. But I believe that still you'll be able to get some new information. Now, you have heard about mission to Mars, mission to Jupiter, mission to Venus, and so on. Missions to asteroids, probably many of you may not have been know that there are such missions. And there are actually such missions. And in fact, a couple of them are undergoing now. And I'll talk about these missions as well. Okay, so this is the outline of my presentation. Can everybody see the slides? Swapna, are the slides visible?
Yeah.
Okay, thanks. So I'm going to just talk about some fundamental aspects of asteroids first, and then talk about a few spacecraft missions to asteroids. Then I'm going to spend a minute or two just telling you about why spacecraft dynamics around asteroids is very different from that around the Earth or around Venus and so on. And then I'll conclude. Okay, first of all, asteroids. What are they and how did this name arise? Well, these asteroids, they grew out of the solar nebula from which all the planets gradually condensed. And they actually are made of the same material, planetesimals, that the planets are made of. So some of these planetesimals combine to form planets, but some of them somehow did not combine to form a planet, and now they're just floating around as shattered small pieces. Probably in a region where there should have been a planet in the asteroid belt. Now, where did this name asteroid come from? Well, in Greek, aster means star. So the Greeks were very much interested in astronomy. They were looking at the sky, and they saw that some of the bodies were stationary, and they were like points. And there were some other bodies which were disk-like, and they were moving around. They were wanderers or planetes, as in Greek they said. So there were planets, and there were also point-like fixed objects called aster or stars. Now, what happened is that after Galileo, he actually not really invented telescope, but he made telescope workable. So after the telescope was discovered, people looked at the sky and they saw some interesting thing, that unlike wanderers, the moving bodies which are disk-like, now they could see some bodies which were point-like. They're point objects, not disks, but point objects like stars. So they were like stars, but not fixed like stars. They were moving. So these new objects that were discovered, let's say around 1600 or so onwards, these were given the name asteroids. They're related to aster or star, but the smaller ones, asteroids. The reason why they were actually small, even though they were moving around, is because the size was small, which at that time people did not know. Where are these asteroids? Now, you see, here I have shown the sun and the planets like the Earth, Mercury, Venus, Mars, etc. And this is Jupiter in its orbit here. Between Mars and Jupiter, you can see tons of, actually millions of small objects floating around, going around the sun. So most of the asteroids are in this asteroid belt. This is called the asteroid belt between Mars and Jupiter. But not all asteroids are in the asteroid belts. There are actually some asteroids which are closer to the Earth compared to the asteroid belt. And there are also some very interesting asteroids. You can see here a bunch of asteroids moving the same orbit as Jupiter. These are known as Greeks. And there are some other asteroids here also moving with Jupiter. These are known as Trojans. I'll talk a little bit more about these Greeks and Trojans in a minute. But most of the asteroids are over here, as you can see, all those points. And as I said, there are millions of asteroids. And some of these asteroids cross the Earth's orbit, and these are called near-Earth asteroids, unlike the asteroid belt asteroids. And there are also asteroids at the Lagrangian points of the Sun-Jupiter system, the Greeks and the Trojans. Now, what are these Lagrangian points? Many of you may not know what is meant by Lagrangian points. Let me just show you that in the next slide. So here, this is the sun, and this is a planet. And let us say that this planet is going around in its orbit around the sun. Now, these planets and the sun, they have interaction between them gravitationally, but also there is motion, there are centrifugal forces involved. So what happens is that there are points close to the Earth's orbit where if you put an object, say for example, if you put an object over here, L1, due to the gravitational attraction of these two bodies, plus the fact that there is some centrifugal forces, the object will appear to be stationary with respect to the Earth. And similarly, there is L2, there is L3, and there are two other points called L4 and L5. These 5 points are called equilibrium points, Lagrangian equilibrium points. So they are referred to as L1, L2, L3, etc. So any object close to this L1 or L2 and L3, their motion is unstable. But close to L5 or L4, if you put a body over here, then that body, due to the interaction of the gravitational force of the planet and the sun and the centrifugal action, that body will be stable in the sense that it will be very close to this L5. It will move in tadpole orbits around L5. So these are the two Lagrangian points. And here, this is Jupiter, this is Sun, and the Lagrangian points are, if you draw an equilateral triangle, Sun, Jupiter, and another point over here, then that third point of the equilateral triangle is the Lagrangian point, the triangular Lagrangian point. So the Trojans are close to this Lagrangian point, and they move around the sun in the same rate as the Jupiter. There are also other asteroids called Greeks at the other Lagrangian point. One is at L4, one is at L5. This is L4, this is L5, the Lagrangian point. And there are other types of asteroids also moving around the sun, similar to the Greeks and Trojans that are Hildas. We will not talk about them now. They're too complicated. So as I said, a large number of Trojan asteroids are in the Lagrangian points. And the first one was discovered only recently in the astronomy time scale, in the sense that the asteroids were discovered in 1600s for the first time, but the first Trojan asteroid was discovered in 1906 in the near Lagrangian point 4. And that is known as Achilles, 588 Achilles. Now, some of you might have read Iliad and Odyssey, and Achilles, you may remember that in the Trojan War, he was a great Greek hero. So many of these asteroids are named after Trojan heroes and Greek heroes. So Achilles was the first Trojan asteroid to be discovered, although it is a Greek. And 588, what is this 588? 588 means this is the 588th asteroid to be discovered. See, initially when asteroids were being discovered starting from 1601 onwards, they were given numbers, 1 Ceres, and 4 Vesta, and so on. Fourth asteroid to be discovered, and so on. So this is 588th asteroid to be discovered. So this is called 588 Achilles. Now, of course, now we have discovered 100,000 asteroids. We don't actually put such numbers anymore. These are initially, they used to be put in 588 and so on. So there are asteroids in the librational points of Sun and Jupiter, Trojans and Greeks, but actually in the Sun-Earth Lagrangian points also there are asteroids which move with the Earth in the same orbit. And one such asteroid was discovered in 1986. Okay, so there are all these asteroids. Why do we study about these asteroids? What do we do with these asteroids, and so on? As I said in the first slide, asteroids are primordial bodies. They're made of the same material that the planets are made of. So if we study the asteroids, we take some material from the asteroids, study them, we may have a lot of knowledge about the early phase of the solar system. So we are interested in asteroids. In fact, some samples have been brought from asteroids to study, and I'll talk about that later. Now, apart from the scientific reason, there is also some other self-preservation reason why we study asteroids. Because the problem is that asteroids impact the Earth regularly, very, very regularly. And some of them are small asteroids which hitting the Earth, some of them are large asteroids. So for example, on February 15, 2013, a small asteroid measuring only 18 meters in diameter, but a mass of over 9,000 tons, it exploded over Chelyabinsk in Russia, and many people were injured, and many buildings were damaged. And about 100 years ago, in 1908, Tunguska region in Russia was hit by an asteroid, and that caused extensive damage. Some people were died. In fact, a large area of the forest was completely burnt, and so on. Now, you might be asking, why Russia? Why not other countries? The thing is that Russia has a very large landmass. has the largest land mass in the world. So if anything comes and hits, probability of hitting Russia is greater than hitting, let's say, Japan. Now, an asteroid impact is thought to be the reason for the disappearance of dinosaurs and many other. And in fact, what has happened is that this dinosaur disappearance happened about 60 million years ago. The scientists believe that a large asteroid came and hit probably somewhere near Yucatan Peninsula of Mexico. And then the impact was so large that there was dust, and it was like nuclear winter for a long time, and many animals disappeared. Such animal extinction due to asteroid impacts has not happened only during this dinosaur disappearance. In fact, many times that has happened. Large asteroids have hit the Earth, and about 75% or more species then become extinct after this asteroid impact. So this dinosaur impact, the dinosaur disappearance or extinction of dinosaur is also related to asteroid impact. Now, a few years ago, I don't know if you remember or not, there was actually some concern. People thought then that an asteroid called Apophis, the name given was Apophis, that will come and hit the Earth. Of course, now we know that it will not hit the Earth, but it will come very close to the Earth, but there will be no impact. But this is a danger. And in fact, regularly, we have planetary defense conferences trying to study means of avoiding disaster if an asteroid comes close and hits. How can we then divert that asteroid so that it does not hit the Earth? So planetary defense is something that is taken very seriously by different agencies and by different organizations. Another thing is money. There are actually companies which were formed to do asteroid mining. In fact, Canadian Space Agency had a program, how to actually exploit mineral resources in asteroids. So this is something that can be done in the future. So this is being investigated, asteroid mining, by government agencies and many private organizations. Some private companies have been set up for asteroid mining. Now, most likely you will not get this material from the asteroid to the Earth. You would probably take this material and use it to construct space habitats or to use it for mission to other heavenly bodies. In fact, because of this danger of possible asteroid impacts, you see, there was a mission by NASA about asteroid diversion. So as an asteroid diversion technology demonstration, NASA carried out a mission called DART, Double Asteroid Redirect Test, 2 years ago. And I'm going to talk about this DART mission briefly after a few minutes. Most asteroids are very irregular shaped, like this potato. They're not nicely shaped like the moon or the Earth or Venus. So they are all very close to a sphere, but most asteroids are not, except the very large asteroids, which are actually very close to spheres. But there are many asteroids, especially the asteroids where missions have landed, they are not spherical at all, very, very strange shaped bodies. But the largest one, Ceres, which was also discovered the first, as a first asteroid, one Ceres, that is almost like a sphere, and it has a diameter of 975 kilometers. It's pretty big asteroid. Though, I mean, it is not as big as our moon, but it's not much smaller. So Ceres was discovered in 1801, and then Juno and Vesta, and then Eros. So these were discovered actually 1800. I think I mistakenly said 1601. It's actually 1801. 1801 was the year where the first asteroid was discovered. And 433 Eros, this is actually an interesting asteroid because the first spacecraft mission to an asteroid went to Eros. And I'll actually mention a little bit more about that mission later. And as I said, there are millions and millions of asteroids. In fact, there are even 25 million asteroids with width greater than 100 meters. And this is a large stone, not a small one. And there are about 200 asteroids with diameter greater than 100 kilometers. So there are quite a few very large asteroids. These asteroids are mainly in the asteroid belt. They're not going to come and hit the Earth. But it is not impossible for a 100-meter size asteroid to come close to the Earth. That can happen. And this is a chart showing, this is Ceres. The diameter is almost 1,000 kilometers, 970. And then the number of asteroids is smaller. This number of asteroids is smaller if the size is larger. So this is number and this is size. If the size is big, number is small. Okay. So this is a diameter in kilometer, and this is the number. And these asteroids, they go around the sun. So just like the Earth and other planets, the asteroids also go around the sun. But they also rotate around their own axis, just like just like the Earth rotates about its own axis once in 24 hours. Asteroids also rotate about their own axis, but they rotate much faster. The largest one, Ceres, rotates once every 9 hours. And when the asteroids are smaller, it is possible that they might rotate faster. Like Eros, which is much smaller than Ceres, this has a period of 5¼ hours around its own axis. So a day in Eros is 5¼ hours long. And these are the period around the sun. Ceres takes it is actually in the asteroid belt, takes over about 4.6 years. Eros is closer to the Earth, takes about 1.76 years. Now, I told you that I'm going to talk about the mission to Eros a little bit later. Okay, now it is time. But before that, I want to tell you that the first spacecraft encounter with an asteroid was not Eros. First dedicated mission to an asteroid was mission to Eros. But before that, when we had this spacecraft Galileo, which went to Jupiter, it actually flew by two asteroids, very close to two asteroids, Ida and Gaspra. Okay, so the first flyby was by Gaspra. So it went to Galileo went to Gaspra on its way to Jupiter. In 1991, took very close pictures of Gaspra, and then Ida, another asteroid. So this is the first time a spacecraft came close to an asteroid, but it did not land in a Gaspra or did not orbit Gaspra. So the first spacecraft that actually orbited an asteroid, just like we have, spacecraft orbiting the moon and Mars. So we had a spacecraft orbiting an asteroid, and that happened in 2000. And the name of that spacecraft was NEAR, just abbreviation for Near Earth Asteroid Rendezvous. So Eros is the Greek god of love. Many of you might know. So what happened is that this is just a picture of Near. But what happened is that when near came close to Eros, it appeared as if there is a heart-shaped crater on Eros. Eros is the god of love, and there is a heart shape. Well, unfortunately, that was just optical anomaly. There is no heart-shaped crater in Eros. So that was actually a disappointment. Anyway, so the plan was that since Eros is the god of love, the spacecraft will arrive at the god of love on the Valentine's Day. So it arrived on 14th February 2000, on Valentine's Day 2000, near the god of love, Eros. So, so that was in 2000. And this was a very successful mission. The spacecraft orbited the asteroid over 200 times, and it gathered extensive data on all kinds of things, about the magnetic field, gravitational field of the asteroid, and the composition, because now we have actually tools to take imaging and then be able to then deduce the composition of the material of that image. So we have such tools and instruments. So near spacecraft gathered a lot of data. And then the goal was initially that the spacecraft near will land on the god of love on Valentine's Day 2001, 14th February 2001. Unfortunately, there were some technical issues and the landing had to be done a couple of days before Valentine's Day. In fact, when the landing was taking place, I was at a conference, and the person who was in charge of all this mission and landing and so on, so he was there. So we had actually a live session where we could see, how it is, the spacecraft is going and landing gradually on the asteroid Eros. It was very, very exciting. Now, after Eros, that was the first spacecraft to go to an asteroid. The next one was a Japanese one. The name of the spacecraft was Hayabusa. It was by JAXA, Japanese Aerospace Exploration Agency. And this is a picture of Hayabusa. And this Hayabusa was sent to an asteroid called Itokawa. Itokawa, this is the name of a professor, actually. So this asteroid was named after Professor Itokawa, who was the pioneer of space studies in Japan. And this was a Japanese mission. So they named this asteroid Itokawa and then sent the spacecraft Hayabusa to Itokawa. And the objective was to return with a sample of asteroid material. So it was launched in 2003, arrived and landed on Hayabusa, on Itokawa in 2005. Unfortunately, it had some technical problems, and it could not bring in as much material as it had planned, though it did bring a few tiny grains of Itokawa, and it did return to Earth in June 2010. Now, I don't know exactly when these tiny grains were analyzed, what exactly were found. I do not know that, but probably not much could be deduced because the material that had been brought back was not very large. The next spacecraft mission was Dawn, and this was a NASA mission. The first one also was a NASA mission near, and then the third one, Dawn, was also a NASA mission. And this is a picture of Dawn. This is a bigger spacecraft compared to Hayabusa, much bigger spacecraft. Now, the goal of Dawn was to go to two large asteroids in the asteroid belt. Vesta and Ceres. Now, why these two were chosen? Because Vesta and Ceres were known to have two different types of constituency. One had more carbonaceous asteroid. The other one was not, more silica type. So that's why these two were chosen, so that you can study two different types of asteroids. So here, this was almost bigger than a ton. So much bigger than Hayabusa, of course, even bigger than Mir. And it went to first to Vesta, but these days, of course, most of the deep space exploration missions use gravity assist. So it actually, the spacecraft Dawn flew by Mars, gathered some energy by the hyperbolic flyby, and then it could go to Vesta. And it did extensive studies for about a year in Vesta. And after that, the mission planners, they had planned that the spacecraft will then leave Vesta and go to Ceres. And it did that and arrived and had a rendezvous with Ceres in 2015. Now, this is a picture of Hayabusa 2. It's a larger spacecraft than Hayabusa. Hayabusa 2 is a bigger one, had many more instruments for image processing, and also it had a LiDAR, a lot of carried involvement in that instrument. So Hayabusa 2 was launched in December 2014, and this was also an asteroid sample return mission. Hayabusa 1, the original Hayabusa, brought very little material, but Hayabusa 2 wanted to bring more material. So it went to an asteroid which is actually named by a number, doesn't have names like Vesta and Ceres, no beautiful names, just a number. So it had a very complicated trajectory, had some gravity assist of the Earth and so on. So it was launched in 2014, went in a very complicated trajectory and reached the asteroid in 2018, June 2018. And then it has come back to the Earth, came back in December 2020 with a sample. And that sample has been analyzed, and they have been able to get a lot of information about the composition and about this asteroid 162173 1999 JU3. So geologists will be able to tell you more about the significance of that. As a spacecraft dynamics, I cannot tell the significance, but they have been able to get some interesting results. That's all I can tell you. And after this Hayabusa 2, which was a Japanese mission, there was another NASA mission. And this is called OSIRIS-REx. These are all abbreviation, OS, etc. Rex. X is for exploration. This was a massive spacecraft. It's 1.5 ton, large spacecraft. And this was also a sample return mission, but as a NASA asteroid sample return mission. It went to an asteroid called Bennu, launched in 2016. When I say that the mission is still continuing, it is, but in a different sense. The mission actually has fulfilled its original goal of bringing sample from Bennu. That has happened. Okay, and in fact, the sample was delivered to the Earth last year. But after that, OSIRIS-REx has been repurposed. I'll show that in the next slide. So OSIRIS-REx was launched in September 2016. and the sample was brought back in 2023. So Bennu is a carbonaceous material, made of carbonaceous material, and it is possible that it may even have some organic molecules, who knows? But the analysis of samples is ongoing. Now, after OSIRIS-REx completed its mission successfully, it was repurposed, as I said. And now what it is going to do is that it is going to fly by an asteroid called Apophis. So the name of the spacecraft now has changed from OSIRIS-REx to OSIRIS-APEX, because it is an Apophis exploration mission. Apophis exploration mission. So the name of the asteroid is Apophis. Now, this Apophis was expected to, well, not expected actually, people were afraid that it might hit the Earth. A few years ago, there was a lot of scare that Apophis might come and might impact Earth. So how we can divert the path of Apophis? So people were working on that. But more detailed calculations have now shown that Apophis will not exactly hit the Earth, but it will come very close to the Earth, much closer than the Moon. So after this close encounter, OSIRIS-APEX is going to fly by Apophis, and then it's going to take all kinds of data. So this study, flyby of Apophis by OSIRIS-APEX, this will allow scientists to study if there were any physical changes after it flew by the Earth. It came so close to the Earth, and Earth is much bigger than this Apophis. Apophis is a small asteroid. So what kind of changes to the surface of the Apophis took place after it had encountered? It hasn't happened, after it will encounter in 2029. What will happen to the orbit of Apophis around the sun? Will there be any change when it comes close to the Earth, and then Earth's gravity affects its trajectory? What kind of changes? Will the spin of Apophis, you see, all asteroids are spinning around their axis just like the Earth does. Will the spin of Apophis be affected? Will there be any quakes, not earthquakes, but Apophis quakes on the surface because of this close contact, close encounter with the Earth? So all these things will be investigated by OSIRIS-APEX up after 2029. Now, this is the final mission that I'm going to talk about. And this is mission to Psyche, 16 Psyche. This is the 16th asteroid to have been discovered. That's why it is 16 Psyche. And the spacecraft is now on its way to Psyche. Now, there are a couple of things I want to tell you about Psyche. Well, you know, when you hear Psyche, you might think that it's got something to do with mind. Well, now psychology, study of mind, etc. But you know, Psyche originally in Greek meant soul. And Psyche was name of a goddess who was a lover of the god Eros. So there has been a mission to Eros. So now there is now a mission to Psyche. Now this Psyche is a very strange asteroid, very different from other asteroids. It has a metal core. It has a metal core. So most of it is iron, nickel, cobalt, and also it has gold and some platinum, a lot of metal. So there has been this talk that, you know, if all the material that is in Psyche, if that can be exploited, by the earth, by the people of this earth, and distributed among the people in the earth, everybody will become a billionaire. There is so much precious material there. So everybody will become a billionaire. Of course, that's not going to happen because it's not easy to exploit all the material in an asteroid like this. But I think eventually a lot of material will be exploited. Now, the thing is that because this has a metal core, so it is similar to many planets. The Earth has a large iron, so it has a metal core too. So it is possible that the Psyche, which could have been a planet, just failed to form. So this Psyche, this metal core, and some other planetesimals, they could have combined to form a planet, probably. It didn't happen. But now it is a metal core. So this mission is called Mission to a Metal World. This is a large spacecraft with large solar arrays and so on. This is the bus of the spacecraft. This is not the real picture. This is just an artist concept. So the Psyche spacecraft was launched last year, October 2023, to a unique metal-rich asteroid. So it's a large spacecraft, much larger than Osiris Rex or Osiris Apex. This is almost 3 tons, 2,750 kilograms, and size of a tennis court, very large spacecraft. And it will reach Psyche in August 2029 and start exploring the asteroid. Now, in 2029, then, there'll be 2 very interesting asteroid explorations. One is this exploration of Psyche, and the other is the study of Apophis that I just mentioned a few minutes ago, after Apophis has a close encounter with the Earth. So this I already mentioned. So these are the missions, past and current missions, and several other missions are in planning stage by different agencies, but they have not flown yet, but they are in planning stage. In fact, there are also missions to comets. There have been missions to comets, and there will be some other missions to comets in the future as well, apart from asteroids. Okay, I don't know how I'm doing time-wise. I cannot see the time.
You're all right. You're all right.
All right.
Yeah.
So I'll take a few minutes. I'm a spacecraft dynamics person, and also there are some astronomy students. So I'm not going to do any heavy stuff over there, but I want to mention 1 or 2 fundamental stuff about why spacecraft dynamics about an asteroid is so different compared to spacecraft dynamics around the Earth or around Mars. It's very different because these asteroids, most of the asteroids, not the largest ones, but most of the asteroids where spacecraft have flown, they have very, very irregular shape and they're rotating. So the gravitational field of an asteroid can be very, very complicated and very time varying. So imagine, you have a potato rotating, and a potato has different shapes. So at a particular time, if you think about the inverse square gravitational force, that of course doesn't hold good. It's a very complicated force. And I'm sure that most people in the audience know about gravitational potential energy, which is 1 divided by the distance. The force is 1 divided by distance square. The potential energy or potential is proportional to 1 divided by distance. So that's for a point to point or sphere to sphere. But if you have an asteroid, because of its shape and rotation, the gravitational potential, which is negative the gravitational potential energy, looks very complicated. You don't have to really look at in the details of this expression. All I want you to see is that it is very complicated. If you have a spherical Earth, you will have mu divided by r multiplied by just 1. Nothing else, just mu divided by r multiplied by 1. And then you have an infinite series for the irregular bodies. And they depend on some constants, C20, C22, C30, etc. And depending on the irregularity of the body, if it's highly non-spherical, C20, C22, C30 will not be small. For the Earth, C20, C22, C30, etc. are 10 to the power minus 6, so negligible. C20 is 10 to the power minus 3, also very small, but not for the asteroids, most asteroids. So because the gravitational potential is so complicated, which depends on the longitude, where the longitude of the point you are calculating the potential, and the latitude of the point you are calculating the potential. So it becomes so messy, and these are all time varying, that calculating gravitational field and then using it to obtain orbital mechanics results become very, very complicated. Many researchers are working on it, and we have had several people working in this area now, working at the Space Agency. But it is very interesting, the dynamics. You can get unexpected results. Sometimes, okay, before I show the results, you see, I just wanted to show, the C20, C22 is, I said that these are of the order of 10 to the minus 6 for the Earth, but for asteroids like Vesta or Eros or Ida, these are actually not too small, 0 0.03, 0 0.04, 0 0.09, almost 1/10. So these are large numbers. So that makes the gravitational field very awkward. And you can have all kinds of different types of orbits. So you can see the direct orbits around Eros, where there was, of course, mission, and there were many orbits. If you are close by to the surface of the Eros, depending on whether you are going direct or retrograde, you can have very different types of results. So these retrograde periodic orbits are very, very nice looking, and you can have very strange orbits around Eros. And in fact, the spacecraft can come and hit the asteroid. This asteroid is Eros. So all kinds of strange type of orbits can arise because of the strange nature of gravitational force. Okay, I just skipped the other one. I just wanted to also show that, about Eros, depending on what is the orbital radius, you can have this crazy rotation of the spacecraft. The orientation can change very much. It can be very stable, small oscillations, or it can actually go crazy, can have very large rotation. So you can have very strange, what is known as attitude dynamics or orientation dynamics of the spacecraft. This will be sort of the final topic, binary asteroids. You see, we're talking about just a mission to asteroids, but there are many asteroids which occur in pairs. About 15% of near-Earth asteroids are binary. Binary in the sense that you have a large asteroid and another small asteroid like a moon of the asteroid going around it. I wanted to show you this is because, that NASA mission DART that I mentioned, that was actually to a binary asteroid. That means two asteroids moving around each other, and the whole system of this pair of asteroids moving around the sun. So they will be moving around each other, just like, imagine the Earth and the Moon. Moon is going around the Earth, so Earth and Moon have their own relative motion, and the entire Earth-Moon system is going around the sun. So same thing happens here too for binary asteroids. And there has already been one space mission to a binary asteroid system, and that is Double Asteroid Redirect Test, DART mission of NASA that took place a few years ago. And what happened is that this spacecraft went to this binary asteroid system. The main one is called Didymos, and the smaller one is called Dimorphos. So there was an impact on the smaller moon, and this was in September 26, 2022, and the path of Dimorphos has been changed. So this was actually a test whether you can go to an asteroid and whether you can actually change the path of the asteroid or not. In fact, the path of Dimorphos has been changed, not significantly, but it is actually large enough that if you have a danger from an asteroid coming, we can do similar things to divert the asteroid. Except that I will be very concerned about that, because when you are trying to change the path by impact, you may break that asteroid into pieces and you will not be able to tell which piece will go and hit the Earth. So it is actually a dangerous, I think it is a dangerous way of diverting an asteroid. There are other better ways of diverting the asteroid than what happened in this DART test of NASA. This is not important. So I'd like to conclude. The first thing that I will say is that asteroids are very interesting celestial objects. They have not received the same type of attention in studying and for study and also for sending missions as planets have. But we may actually learn much more through asteroid missions. And I described some mission to asteroids, and many interesting missions have taken place, and some are in the planning stage. And when you try to design a space mission to asteroids, you have to do much more analysis related to the dynamics, because the dynamics, both the orbital mechanics as well as the orientation dynamics of spacecraft, can become very complicated. Your control system that you are going to design also have to be designed properly. The trajectories have to be designed much more carefully by doing much more analysis and so on. So mission to asteroids are very interesting, but the dynamics are also very interesting and challenging. So that's all I have to say. And I'll try to answer any question that you might have. Thank you very much for your attention.
Thank you, Professor Misra. Okay, thank you so much. Really appreciate the, Professor, you can see probably the classroom too, a little bit.
Yes, I can see the classroom.
Okay, perfect. Okay, everybody wave. So we would like, we'll start our Q&A. For the Q&A, could you come down to the mic to ask the question? So I'll start. Are there any Canadian missions to asteroids planned or Canadian supported missions planned, Professor?
No, there are no Canadian missions planned to asteroids or even to any planets, but Canadian instruments are always used in many missions to outer planets or asteroids, etc. We build instruments, but we don't have any planned mission to any asteroid or planets.
You mentioned the complex orbital dynamics around asteroids. So if you're planning a mission and you haven't been to the asteroid before, you can't really plan the orbit. You just have to stay far away initially?
No, that is actually not completely correct, because after all, we send missions to, let's say, Eros, and nobody had gone to Eros before, but the spacecraft near went, orbited Eros, landed on Eros. So we can get an idea about about the gravitational forces and about their parameters by other means, by imaging, by taking pictures, by doing the some kind of analysis of its possible concentration and so on. So we can prepare a model, we can build a model of for the asteroid, and then based on that model, we can estimate the gravitational field. It will not be accurate. After flyby, we can actually then probably make it more accurate. But we do have some idea about what will be the gravitational forces. So we have sent so many missions, and there is always a first time. We had never gone to that asteroid before, but we could actually learn orbital dynamics about it. But what also can be done is that you don't go and land on the asteroid right away. In fact, you see, when Eros went, Eros orbited. I'm sorry, not Eros went. When Near went to Eros, Near orbited Eros more than 200 times at higher altitude, but gradually came also down, and could then make a better model of the gravitational field of the asteroid, and then it landed. So you can actually make corrections, updates, etc. But it is possible to have some approximated gravitational field even before going to the asteroid.
Hey, thank you.
Hi, Professor. Very interesting talk.
Thank you.
You mentioned, this is a question about diverting Earth, diverting near Earth asteroids that are going to possibly hit the Earth. And you mentioned that the impact method was not your favorite method because it could break up the asteroid into lots of bits and whatever. Can you talk a little bit about the other methods and the one you would prefer?
Well, there are several other methods that have been proposed. One is that you can have a gravity tractor. So you can have another body, and that will provide some small gravitational torque, small forces, and then that small forces over probably a couple of years will change the path of the asteroid slightly. People have also proposed of using tethers, and you can connect a long tether to the asteroid, and there will be an end mass, of course, at the other end of the tether, and then you deploy the tether, and then it will rotate because the asteroid is rotating, and then you cut the tether. That way, there will be some momentum exchange, and you can actually change the path of the asteroid. Studies have been done using this particular method, and people have also thought of putting maybe large solar sails. But you see, solar sails, of course, have only small perturbations on the orbit. But you have to know that an asteroid is coming to hit the Earth sufficiently ahead of time, then only you can put the solar sails to change the path of the asteroid slightly. Because solar radiation pressure also can change the path. In fact, solar sailing has been proposed as going to another planet by using solar sails. So solar sailing also can have some impact. So there are various different methods people have been thinking of. But if you put let's say it's just an impactor or an explosion, then it is too risky. You cannot predict what is going to happen to the different pieces that will be produced from this explosion. So that's my concern. But there are other less dangerous ways of diverting the path of an asteroid, but all of them take time. All of them take time to change the path of the asteroid significantly to avoid impact. But even if you explode if you actually have an impact and cause an explosion, that also does not change the path of the asteroid very quickly anyway.
Could you comment a little bit on like how much time before a potential impact you'd have to start doing this? Because I've
It will
read,
be in terms of years. It will be years, at
But
least 2 to
with-
3 years. Yeah.
with the discussion about, say, Adolphus, it took us a long time to determine that it wasn't going to hit the Earth. And, so I guess you'd really, really need to know a lot about its orbit before you start deflecting it, because you could deflect it on a non-collision orbit and put it on a collision orbit.
That is also possible. Yes.
Yeah.
Yes.
Okay.
That's
Thank you very
possible.
much.
But that's yeah, you have to do more accurate calculations. So we are getting better and better at predicting trajectories from observations.
Thanks again.
I have one last question, Professor Misra. So we
Okay.
talked about Psyche, and you mentioned it was metallic.
Yes.
How does one know from Earth which asteroid is metallic, or they selected Bennu? Like how do you come to that determination?
Yeah. Okay. This is something that I'm really not very knowledgeable about, but I do know one thing, that we can observe celestial objects, and from various data, like for example, what kind of radiation or at what frequency they are radiating, and that tells us what kind of material they have. And we can also find out, even in stars, what are the composition of stars, and they're very far away. So there are optical methods, there are chemical analytical methods, but basically they're by analyzing spectra. And I do not know really from spectroscopy how they figure this out, but these are all spectroscopic methods.
Okay, wonderful. No, so this has been great. Thank you so much. Professor Misra, your talk has been very well received. I'll share the recording when it's available. I'll share the link. Thank you so much for taking your time, and all the best on the flight back home.
Thank you. Thank you.